Hello and welcome to my presentation on the Sapflowmeter. This is going to be a visual multimedia presentation by Jonathan Fookes and narrated by me, Brett Stoddard. So the team, like I already mentioned, for this senior project was made up of me and Jonathan. So because we had a two-man team, there's a lot of overlap in what we did, but generally Jonathan was in charge of implementation and I was in charge of a lot of R&D. So that meant Jonathan Fookes took over the power block, the PCB board design, and wrote all the code, where I did the background research, worked on the probes, and was in charge of all the testing. So the background, what is Sapflow? So Sapflow, like every tree has sap, and sap generally flows up it. During this called transpiration. This is analogous to the number of calories an animal consumes, as the quantity of water transpirated has a direct relationship with this scientific measurement called gross plant productivity, which is pretty much just the amount of photosynthetic activity taking place in a plant, therefore the amount of sugar it's generating. It's almost like a metabolism. This is an important number to researchers and biologists who want to model ecosystems and tree activity. It can also be used to measure water availability. That's why we believe it has commercialization potential as a sensor in a closed-loop irrigation system, such as the one shown, where there's one sensor put in a management zone, and then it gives feedback to an irrigation controller, which disperses water accordingly. And yeah, so a management zone usually would be farmer defined, and that's based around soil and geological features. So our Sapflowmeter is significantly cheaper than commercial versions. So our probes cost about $50 versus theirs $700. Ours full system's $300 versus theirs for $1,400, and this includes a logger with cellular capabilities, but it does not include a solar panel. And is ours open source? Yes. Is theirs open source? No. This is just one Dynamax, their thermal TDM, I believe, probe, and yeah, so by reducing the costs, this opens the door to be more accessible outside the scientific setting. Our system was built using simple temperature sensors and just hobby-grade electronics, so it's a lot more approachable by the general community. So our system consists of really trying to do math, 5 parts. There is these, starting right to left, there is the sap flow probes. So there's 2 temperature sensors and 1 sap heater. And the sap heater is controlled by a heater controller, which is right now a switching relay, but it could be a MOSFET. And then, yeah, everything is controlled by the board. The sap heater controller is triggered by this board. And the sap temperature sensors are grabbed by this board. Yeah. So the probes design themselves to look like this, where there's 3 prongs with a temperature sensor, and a heater. And this heater gives off a heat pulse. And as the water flows up the tree, this heat pulse will be carried disproportionately to one heater probe over another. So this temperature will be higher, this temperature will be lower, and then looking at the ratio of the temperatures, you can figure out the amount of sap flow. It's analogous to sap. Nope. Unselect pen. Alright, so really quick, here is going to be a demo video. If it pleases the Microsoft PowerPoint overlords. All right.
The system as it exists in its final form is all powered from the battery right here. The battery brings all power to the microcontroller, the Feather M0 with LoRa radio, which is connected to the power relay, which is the heater controller in this case, and the heater controller runs to the heater. We have a backup SD card for saving data that is part of the board block, and then to the back, power is sent to these temperature thermocouple amplifiers, and we have our sensors right here, temperature sensors. These units right here all together make up the probe that is inserted into the tree. All data is sent through LoRa radio to a database through this antenna here, and all of these are housed in the system. The way it works is you turn it on with the battery, you see the lights turn on, and you hear the heater controller begin to run. The clicking and the turning on of the red LED shows that power is being sent to the heater probe, which is now hot to the touch. Inside the tree, the probe works by calculating a differential temperature between the two sensors, the bottom serving as a reference, and as sap flows up through the tree, it will carry heat up to the top temperature sensor. This data can then be used to calculate sap flow in grams per hour, and just in case we get any wireless connection issues through LoRa, we have everything saved right here on our backup SD drive. A 3.5 volt regulator can be seen here, and that is just to keep voltage consistent for all of our thermocouple devices back here, making sure they all get the proper amount of current. And that is how the system exists in its current state.
All right. Thank you, Jonathan. Moving on, we talk about the success and the successes we've had with testing. So here is shown a vat of water, which multiple probes have submersed, and a large reference probe. We used the Opens Labs Fookes thermometer to do this. We collected data from all of them and then calculated the mean average error from them. And and this was used to determine which probe is the best. We calculated thermocouples, T-type, K-type, a LMT70, and thermistors. We found that the thermocouples were the best, with the K-type pre-built from Adafruit just barely beating out the homemade T-type versions. So now we want to test in a log. This is a kind of a future goal, but we have successfully pushed water through a stem using a pressurized hose that goes up to around 10 psi, and then water just drips out the other side. And the idea is you can put a scale, collect the water, and then by looking at the timing and the weight of the scale and the measurements on the sensor, you can figure out the flow of water and calibrate the probes, and also compare the probes against the commercial Dynamax, which unfortunately hasn't arrived. The plan is to do this before we graduate, but at this point we've hit some setbacks, so we'll see if that happens. Another thing is to build to spend more time building an RTD probe. So RTD has the highest potential in terms of accuracy for any temperature sensor, and we recently figured out a way to get even thinner boards from Osh Park that get it down to 1.36 millimeters in diameter as opposed to 1.87. This is pretty significant, and will have a pretty good impact on the tree, but we're still figuring out the electronics because RTDs require an amplifier to get the sensitivity we need. So there's a lot of testing going on with that. Looking forward, we also built a PCB board that we want to house everything, but has the different amplifiers and the electronics change for the temperature probes. Things will change, but we have that available. And then also we want to do just more and more and lots of experiments on the tree. Like we want to do multiple logs, we want to do multiple geometries like the TDM versus the HRM probe, or two or three probe designs. We want to look at compare commercial probes. We want to compare like different diameter trees ideally, but also looking at different areas in the tree. And this calibration procedure is going to be about a scientific paper's worth. Great. So, well, thank you for coming to the presentation. Good luck with the project.